All right, welcome to day 4 of x86-64. As promised, we're going to start off on exploiting Linux for penetration testers. Yep, I noticed that. So just to let you know, I'm streaming just this first module out to the Off by One security channel. So if you hear me say anything odd, just kind of sharing a module with folks that can see what it looks like. So welcome to all those listening online and all those online for class and also folks in the room. We are going to start out this morning going over low-level items such as memory, processor registers, how virtual to physical address translation works, how linking and loading works, a bit on assembly and reversing. So many different items we'll be diving into today. And I see a question on this channel. Different exploitation types. We'll certainly talk about some different ones. I'm happy to talk about any one that you have questions about. For the most part, though, in today's session, we'll be looking at exploit mitigation bypasses, like how to get around if ASLR is on, how to get around stack canaries when they're compiled in, which is pretty typical, how to get around data execution prevention using return-oriented programming or other techniques. So today's the focus on the Linux side of the house, but this first module is not about exploitation, though I'll reference some items. It's about understanding this low-level type of items and things in architecture that we need to be able to get through the rest of the material. So I'm just going to dive right in because it's a pretty heavy and long module. And we're just going to jump straight into the processor registers and the cores. So obviously, most of us have multi-core processors, and it's been that way for quite some time. In some examples that I'll reference, I'll just say, let's imagine there's a single core CPU, just to explain items that it'll make a little less complex doing it that way. So when you think of memory, physical memory, your brain, of course, is going to go to RAM, which is pretty typical. But there are different types of memory, and the closer you get to the processor cores, obviously the memory is going to get smaller, but it's also going to be much faster and more directly accessible. So if you go into a processor core, there's going to be general purpose registers as well as other registers that we'll get into. These are, so for example, if you're running a process that's multi-threaded and you're utilizing multiple cores, all fine and good, there's a set of registers again on each one of these, and we're going to talk about the general registers versus flags registers versus the instruction pointer and debug registers, control registers. There's all different types of them. They are either 16-bit, 32-bit, 64-bit, and even larger than that with some MMX registers and others. So originally, let's say we had 16-bit architecture, and then when that got extended out to 32-bit architecture, now you've got registers names like EAX and EDX, as where before it was just AX and DX. And we're talking about Intel or x86-32 and x86-64 bit architecture. Obviously, we could talk about ARM and MIPS and other ones as well. But on 64-bit, so on 16-bit, you've got AX, for example, that's the accumulator register. 32-bit, that would be EAX for extended accumulator register, and then 64-bit, you've got RAX for register AX. We're going to go through kind of working our way outward from the inside. So if you can imagine these processor cores having these registers integrated physically onto them, they're doing things like arithmetic, they're holding pointers to different types of data. You've got instructions, you've got data, of course, there's different types of cache associated with them depending on what they are. You've got translation look-aside buffers, which are going to store recently resolved virtual to physical addressing. And as you work your way out from these registers that are quite small in comparison, as you work your way outward, you get to like L1 cache and then L2 cache, and it's getting larger and larger as you go out. You've got, again, data cache, instruction cache, utilized for different things. And then you've got this, in this example, you've got a shared L3 cache, again, getting larger, and this being shared between all the cores, as where the other L1 and L2 cache are going to be integrated into the core. You work your way outward from there. Eventually, you're going to get to RAM. And then, of course, you can page out to the hard drive, and you have other options as well. If it feels like we're covering anything from a high level, we're about to get a lot lower. So we've got these processor registers I was just describing. On 32-bit Intel x86 architecture, you've got 8 general purpose registers. They're listed up on the screen at the top. I'm not going to talk through each one of them now, but we are going to cover the notable registers as we go through the next couple of slides. The E, again, stands for extended. So when you see that, you know it's a 32-bit register. Even if you're on a 64-bit process, though, you're going to see references to smaller registers. You will see on a 64-bit process, RAX might be referenced as well as EAX in another instruction. you can utilize portions of the register. Certain registers, you can actually take the lower 32 bytes or bits, of a 64-bit register. You can take the lower 16 bits. You can take the lowest 8 bits or the second to lowest 8 bits. We'll talk about how that works in a moment as well, and that's only on certain registers. 64-bit, we've got 8 additional general purpose registers, R8 through R15. Think of it as having a lot more shelves in a closet available for you to use for storage and other purposes. Segment registers are 16-bit registers. Those had more notable use in older architectures, but you'll still see them used, especially some of them like on Windows, for example, the FS segment register and GS segment register, 32 versus 64-bit, would hold pointers offsets to structures, for example. Like in userland, the thread information block, you can always see by looking at the FS segment register, it holds the offset to that particular data structure. And we'll talk about this more as well coming up, every thread, let's say on Windows, and within a process, gets its own stack. It also gets its own TIB, thread information block. And you can always see it by looking at FS, segment register. Offset 0 would be the start of that structure. And at the very first offset within that structure is going to be a pointer to the structured exception handling location or position on the stack. And then you can work your way down through various offsets, and we'll see it soon. There's different things at different offsets. And again, this is Windows specific. Like FS offset 30 is going to be a pointer to the process environment block. If it was 64-bit, this would be the GS segment register, and the offsets might change a little bit. So some segment registers have notable use. If you're writing your own operating system and loading things up, you probably use them as well. There's descriptor tables and such, like global and local descriptor tables that you would work with. The flags register is, you've seen it already in another section when we were looking at fuzzing, for example, where you might see some comparison happening within a block of code within a function that says something like compare 0 to what's stored in the ESI register. And if those are equal, so if ESI holds a 0 and we're comparing it to 0, that's going to be true. So therefore, we set the 0 bit or flag within the flags register. And then you're going to have a edge or branch that's going to say jump if 0 or jump if not 0, jump if below or equal. So various arithmetic and comparisons that are going on are going to set the state of the flags register in different ways. So there's going to be a 0 flag, a negative flag, a carry flag, and various types. There's a lot of Boolean operations that occur. Like, for example, a test instruction does a bitwise AND operation. And we can test specific bits. Let's say, for example, you're dealing with, and I'm making this up, but think about the TCP header and how you've got the SYN flag, the push, ACK, urge, fin, reset. Those flags are all based on their position within a certain number of bits. Bit mask, bit flag, whatever you want to call it. And if we want to test to see if a certain bit is on or flag is on, we can say test and then a specific value like 32 against that binary position within a byte, for example. And you're going to be able to find out if that bit is on or off. You could also OR it or AND it. You can turn them on, off, but you're testing it. You're checking to see if the bit is on. And based on the result, the appropriate flags get set, and then you hit a conditional branch that says jump if below or equal or something else. You also see a test instruction oftentimes. I'll give you an example. If you call heap alloc, which is a Windows function to do allocation on the heap, of course, self-explanatory. Often, typically, when you return back from the call to heap alloc, one of the arguments it wants is going to be which heap that you would like to have an allocation in, like the isolated heap, for example, and also the size. What's the size of the allocation you want? And you're supposed to get returned back to you, just like with malloc on Linux, a pointer to the allocation, the data portion of the allocation. There's going to be metadata behind that. And if the allocation was successful, then the accumulator register, let's say RAX, R-A-X, is not going to hold 0. It's going to hold a pointer to the allocation. If the heap alloc call fails, then the accumulator register would likely hold like a 0, which means when you test it, you're going to get a result that's going to be different than if the allocation was successful and there was a value, a pointer in that register. Because as you'll see, the accumulator register is typically what returns back something like a status code or a pointer to an allocation or whatever else. RAX is a pretty significant register in relation to x86 architecture. The instruction pointer is the coveted register, of course, because it's also known as the program counter. It holds the virtual memory address where execution will next occur. When you get to a memory address and the execute flag is on and you go to execute it, it goes through an execution cycle. And at that point, the instruction pointer is going to point to the next address where execution will continue after that cycle completes. So if you get control of that thing, of course, and you've got the execute flag in the area where you're pointing it, then you obviously have control of code execution in that process. Control registers are another example. They are used for different things. One notable example is that control register 3, and I did a stream last Friday actually, and I had Daniel Fernandez on, who is one of my co-authors on the Gray Hat Hacking book series, and he wrote chapters on hypervisor exploitation and debugging. And he explicitly showed that control register 3 holds a pointer to the start of the page directory for a given process. The page directory is very important because that's how we do virtual to physical address translation. You have PLL mappings and such, which is the metadata and structure associated with the page of memory, and different flags in there, like the NX flag for no execute. And we're going to walk through how that works coming up here momentarily. And what I'm talking about is the virtual to physical translation process. And it's a little bit different on 32-bit versus 64-bit. I'm going to demonstrate 32-bit just because it's easier to draw out and makes more sense. There's a really great book called What Makes It Page that is like several hundred pages, primarily on 64-bit memory management and address translation and things like that. So it's a really useful book if you're really interested in the lower level part of that. But another example, a control register, like when you're under the context of the kernel mode, ring 0, on a Windows system, I forget which control register it is, but there's a register that would hold a specific bit that has to do with supervisor mode execution prevention. And if you can flip that bit as an attacker, then you're going to get around some mitigation. There's so many mitigations that we're going to talk about over the next couple of days that get in your way. Thankfully, to those of us who do write exploits for the Windows operating system and the applications on that system, most of the mitigations in association with exploit guard are not turned on by default. As we go forward, each Windows version or update that comes out, sometimes there's new mitigations that get turned on by default. Like a long time ago, in 2005, I think it was, XP Service Pack 2 came out. I think it was that year. And DEP was introduced. Data Execution Prevention was introduced way back in like 2005, whenever XP Service Pack 2 came out. ASLR didn't come out until Vista. And it wasn't until Vista Service Pack 1, I think, I could be off by one or two, that DEP was turned on for all programs and services by default. Up until that point, you had to opt in for DEP for any third-party application that you would install. Windows Essential Services and such did participate automatically in DEP. But you got to turn this stuff on, and the newer mitigations, there's more of a likelihood that they could potentially have a negative impact on a production application or service. And Microsoft doesn't want to turn those mitigations on if there's a chance they could break things. They leave it up to the administrator for you to go understand how that mitigation works, do your testing, and then turn it on if it makes sense. Examples would be arbitrary code guard or bottom-up ASLR, or newer ones like shadow stacks and control flow enforcement technology. There's newer ones as well, like having to do with virtualization-based security. You have HVCI, which is the hypervisor code integrity, and things that are occurring in ring -1. You've heard of the secure kernel, of course, and isolated user mode processes or trustlets, and how you need to go, you can't just jump from the typical Windows kernel in ring 0 over to the secure kernel because it's being managed and governed by Hyper-V. And then you've got secondary level address translation and all these things you have to deal with in a broker that allows you to go between the two. An example of the first process or service that I think ended up as an isolated user mode process is Credential Guard. where when you turn that on, the LSAS process no longer in userland has the credentials in there. It's been moved to another process running as a trustlet or IUM called LSA ISO. And inside there are your encrypted credentials. So Mimikatz is going to fail then. So as we go forward, more and more of this stuff starts to evolve. Things get more secure. Mitigations get turned on. I kind of went down that little bit of a rabbit hole there because we were talking about control registers and how I mentioned SMEP can be turned on or off, potentially on a version of Windows by flipping a bit if you know where it is. So let's go through each of the general purpose registers, with the exception of R8 through R15, because those are truly just general purpose registers that compiler can use for whatever it wants. Same thing with an assembler. If you write your assembly and you assemble it with something like NASM or DASM into machine code, you have obviously direct control and access to the registers and can tell them whatever you want to do, as where a compiler is going to make that decision for you. And optimization, mitigations, other factors may change the way in which you would have preferred the machine code to look or something to happen. That's why assembly is so powerful, because you can specifically say how you want something to be done. We'll talk about that a little bit more soon. But anyway, AX is the accumulator register, often seen as the primary calculator for the processor core. But it can do many things. They're called general purpose registers because there are, in x86, there's an instruction set that's quite large. And it's a variable length instruction set. There's one byte instructions like a NOP or 41, which is increment ECX, which is also a capital A in ASCII hex. There's 2-byte instructions, EB06, that's jump 6 bytes. EB is jump, that's the instruction, 06 with the operand. And you can put whatever value you want there. There's 3-byte instructions, 4, 5, 6, 7, 8, 9, and beyond. So it's variable length, unlike ARM, for example, which is 4-byte instructions. Unless it's a thumb instruction, then it's 2 bytes. This makes something like return-oriented programming very fruitful and usable, because you can index into anywhere that the code the execute permission is on. You can index into any byte offset, whether or not it's an instruction that was intended by that process. It doesn't matter, because it's variable length. You can index into offset 3 within an existing instruction, and as long as how that machine code, as long as it gets interpreted as a valid instruction, opcode, then execution will continue, and you maintain control by having that end with a C3 byte, like a return or some kind of a jump or something else. Yes? So the question is, are these instructions standardized across all chip manufacturers? Yes, if they want to be x86 or x86-64, then the instruction set's going to be the same. Now, some processors have instructions that another one might not support. Like, remember when VTD came out for virtualization support with the processor? Some processor makers didn't support that, so there might be some limitations. But the instruction set itself as a whole, yes, it's the same between. But if you write some code for ARM, you can't run that on x86 because it's in a different instruction set. So AX, as I mentioned as well, is what's going to return back something if you're expecting something from a caller. You know how when we declare, do a function declaration and we say int or void or something like that, you're specifying whether or not you're expecting something to be returned back. That might just be a status code, like a 0 if everything's okay, or a 1 if there was an error. You might be expecting back a pointer to a memory allocation or something else. The DX register is a data register. It's a general purpose register, and it's just an example of assembly over there on the right. But on 32-bit, you would sometimes see it work with EAX on calculations, since we have a 32-bit max width there, and on 64-bit we've got 64-bit width. So it's a little bit not difficult, but I'm going to explain it by example as to why I'm saying, or what it means that these are general purpose registers. Let me finish the last couple on this slide though. CX is the count register. Historically, more notable use in the past, but you might have something like an iterator variable in a loop. I equals 0, and you're going to keep iterating through that loop until you max out at 10. Then you break out of the loop. You may have seen the count register holding that iterator variable. But you mostly see it just as a general purpose register, and I'm going to write out that example in a moment. BX is the base register, and that's truly just a general purpose register. Again, think of opening up your pantry in your kitchen and there's a bunch of shelves. You're going to put the stuff that you use more often on the shelves that are more convenient. The super high shelves are going to have things you don't need as often. That space is available, we like it, but we don't always need it. On 64-bit, we've got those 8 additional general purpose registers, which is super helpful. It also allows us to not have to push arguments so many times or so often onto the stack for a function call or system call. Because if you push something onto a stack, that's writable memory, and if there's a buffer overflow opportunity, obviously that's could be victim. As opposed to if we put our arguments into registers, which we do that on both 32 and 64-bit, we just have fewer registers that are general purpose on 32-bit. But it's going to be safer potentially to pass them via registers because you can't just overwrite a register. You'll improperly hear people say, I overwrote EIP or I overwrote RIP. No, you didn't overwrite RIP or EIP. You overwrote maybe a return pointer and then the return instruction executed, redirecting the flow of execution to that address. But you can't overwrite a register without opening up the core and start, I don't know, you get a pen or something. But it's just terminology to be correct. So those are general purpose registers. We got 4 more that we're going to talk about. These 4 registers are the ones where you can actually access the lower portion of that register. For example, if you're talking about EAX, that's the 32-bit register, all 4 bytes. You could say AX, then you're only referencing or accessing the lower 2 bytes. You could say AL, that's accumulator low. That's the lowest byte in the register. Or AH, which is the second to lowest byte in the register. 64-bit, same thing, only on these registers though. You can't do it with the other ones. And if you need to get the highest byte value as opposed to the lowest byte value, you're going to have to use shift operators and stuff like that. But let me draw out what I mean. We're going to go to this slide, and let me first draw what I mean by general purpose. And for those of you watching online, I'm teaching from an old laptop is why you're seeing Windows, an outdated version of Windows here. So the example I'm going to show you is, somebody asked about use after free. So let me explain use after free exploitation at the same time I show you what general purpose means with regard to registers. So let's say that we've got a C++ object here, and Windows uses a strange invasive method of smart pointer implementation on C++. If you're familiar with that language, it's a bit odd that they chose that method because it makes it exploitable if the conditions are right, and you'll see what I mean in a moment. So let's say this is a C++ object, so it's instantiation from a class, and typically you have functions, and if it's a standalone function, we have functions so that we don't have to repeat our code all over the place. We can call that function that does a thing, and it returns back to us whatever we want, or whatever it's allowed to return back to us. And it's just like a template. It doesn't store anything. There's no persistence. You get in, you get out. But if you want to have something that, like an object, that you can take actions on that object, and that object stays resident in memory for as long as it's supposed to, you would use a class in that example. So you instantiate an instance of a class. Silly like computer science example, you have a dog class, and from that dog class you've got different attributes like the fur color and the gender of the dog and the size of the dog and the breed of the dog. And this is like, think of a blueprint or a template, and from this template you can instantiate instances of a dog, and you get to select, I want a Rottweiler, and I want all these different attributes to be set. And then when you instantiate that object, depending on the class, there's going to be these various methods or functions that travel around with that object. You can say Fluffy, which is the dog's name, I guess, dot speak, and if that's a supported method, the dog will speak. So pretend that this is one of these objects. And I'm not going to go any further into explaining what classes are, but there's derived classes and inheritance. There's virtual functions that might be used. There's runtime and compile time polymorphism. There's all these factors. But the way that Microsoft did it, you've got the object, and at the very beginning of the object, if virtual functions are being used, which is very common, like saying in a browser or in a big word processing application, the very first variable within this object is going to be a virtual pointer, v pointer. And that's going to point to a virtual function table. Because of the way Microsoft implemented smart pointers, the next member here, I shouldn't call it a member, but their variable in this object is going to be a counter. So CTR. That's going to count and maintain track of the number of references that are currently referencing this object. And so let me give you an example. If you have a browser DOM and on that you have JavaScript that says, I want to create a button, that JavaScript is then going to call down to a C++ class that's going to be called CButton, and there's going to be CButton : create element, and there's a static size associated with that type of object, and then it gets created. You might have a button that is inner HTML, and you could then say click me. So the button says click me now inside of it. When you do stuff like that, or maybe you make a table, you use TD and TR, you're going to have references now. Another example would be like if I append as a child some type of object as a child node to a parent node, there's going to be references there. So that's what's going in the counter. And the idea with that smart pointer implementation is if you can decrement the reference counter down to 0, that means that object is no longer needed. It can be recycled, given back to the heap manager so we can reuse it. So as an attacker with use after free, I want to somehow figure out a way through weird JavaScript or other means to decrement that reference counter to 0 prematurely. If that happens, then the process still needs that object. And if a reference to that object is made at some point, it's going to, if it's still freed, it's going to crash the process. If it's been recycled and it's back in use, it all depends on what's there now. Because what's going to happen when it's a virtual function call is the following assembly. This is an example. It would say something like move into, let's do RCX, comma, dereference RDX. My handwriting's bad, but you get it. So what this would mean is that there's an object pointer that RDX holds the pointer to. So RDX points to the object. This is the C++ object. And by doing this, executing this instruction, we're dereferencing, meaning we're going to what RDX is pointing to, and we're taking what's there and loading that into the RCX register. So now RCX holds a pointer to the virtual function table. So we've got this big virtual function table now. It's variable in size. It all depends on how big it is. So there's going to be slots within this virtual function table. I'm not going to draw all of them, but let's pretend there's more. So this is the VF table. And at these slots are going to be pointers to the functions. So this could be a pointer to, I'll just put virtual function 1. That's going to be offset 0 within the table. Then a pointer to virtual function 2. That's going to be at 0x8, because we're 64-bit. And then we've got a pointer to virtual function 3. That's going to be 0x10, and dot, 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 and however long it is. So the next assembly that would, the instructions that go to be executed, is going to be something like, if I want to load virtual function 2, and that's the one I want to call, we'd say something like move into, I'll just say R15, dereference RCX plus 8. That means go to the virtual function table, because that's what RCX is pointing to, go plus 8, grab virtual function 2, the address of it, load it into register 15, then the next thing you're going to see is a call to R15. Now, control flow guard would likely be there, which means before you do this, you're going to actually check to make sure the address you're going to call is valid within the bitmap that control flow guard has access to. Basically, it's a bitmap of the entire memory, or the entire image, and it's broken up into chunks. And if the address being called is within a a plotted area on the bitmap that has valid function entry points, it'll allow execution to continue. If the address you're trying to call is not within one of those areas in the bitmap that is marked for, that has various function calls within that region, you're not going to get to call it. It's trying to stop you from doing like return-oriented programming, things like that. But that's a standard virtual function call. And my point, look at the registers I used. That's arbitrary. I just randomly selected RCX, RDX, and R15 in this one. Could it have been register 14? Sure. As long as it makes sense. That's the compiler's job, of course, and the assembler to put that together in order for it to make sense. Now, use after free, going back to that one more time, if I'm able to prematurely decrement the reference counter to 0, and typically in JavaScript, we would collect garbage to make sure everything gets freed up nicely. Some languages have garbage collection, some don't. Then that's going to make sure that the object that we got prematurely freed, that allocation, is now available to be recycled. Now, on older versions of Windows, it's always going to be last in, first out, which means the most recent allocation that gets freed is the one that's going to get returned back and recycled first. That depends, though, on the size, because there are these things called bins. This is a heap thing. Linux does it one way depending on various heap implementations like dlmalloc, tcmalloc, jemalloc, phkmalloc, ptmalloc. And then Windows has their own implementation. There's a front-end heap allocator and a back-end heap allocator. On Linux, we've got things like fast bins, and we've got tcache bins. On Windows, we've got a look-aside list, which got replaced by the low fragmentation heap in userland a long time ago. And then you've got things like the low fragmentation heap and segment heaps and other things going on. So the idea of bins, let's use Windows as an example, since this example I'm drawing up is Windows-based. The way that Microsoft did it was to take the bin number, and there was bin 0 all the way up through 127, and you multiply the bin number by the block size, and the block size was 8. It was always 8. So 8 times bin 10, 80 bytes. 80 byte chunks that have been freed and are available to allocate are stored in bin 10. It's a doubly linked list, and it's changed and get optimized over the years. Now there's like list hints and counters, and like originally LFH was, as long as there was, I can't remember, was it 16 or 18? I think it's 18 consecutive allocations of a particular size, then that chunk size is going to get managed by LFH that triggers. So there's a counter watching that. And that would be a heap type of 2, which would be LFH managed heap. So bin 100, 100 times 8 is 800. 800 byte chunks would go in bin 100. Doubly linked list, forward pointers and backward pointers pointing to all the different free chunks that are available in relation to that list, to that bin. So that's how you do the little maths there. What happens when you get to bin 127? Well, 127 times 8, I think it's 1016 bytes. So 1016 byte chunks go in bin 127. Chunks that are larger than 1K or higher would go into bin 0. Linux has an unsorted bin and things like that as well. All the allocators are different. It's not a Linux thing, it's a heap allocator thing. And then if you want like a really large allocation, you're going to call a different function. There's different functions, they handle different sizes, different things for different things. So, okay, isn't it safer though to randomize the allocation from a free list? So if an attacker is able to prematurely free a object and they want to be able to, because what the attacker wants to do is they want to prematurely free this object and immediately do an allocation that's the same size of the freed object so that they can fill that slot. And what they would put there is something malicious. They would do like a JavaScript string allocation, and they would unescape the Unicode so that they could control the first 4 bytes or 8 bytes. And that means when that assembly gets executed there, it's going to call the V pointer that points to whatever the attacker wanted it to point to. This is a malicious object now, and a malicious virtual function table. That's how we gain code execution and use after free in one example. So my bad analogy, I used this at RSA years ago at a presentation because there's varying levels of technical backgrounds when people come to a talk at RSA. There might be some new people, might be some super senior people. So you kind of want to use analogies that are going to work for everybody. I don't know why I came up with this one. It's pretty grim. But let's say that you at home, you live with your spouse and you have one child. So there's 3 family members in that household, and you have a dog. So you got you, your spouse, and one child and a dog. So there's 3 references to the dog because there's 3 of you. You each have a reference to that dog. It's a dog's reference counter. So if I go out on a trip and the dog passes away of old age, of course, it's a happy life, not a sad thing, still sad. And the dog passes away, my spouse and my child may decide, hey, let's not tell Steve that Fluffy passed away until he gets home because we don't want to make him sad on the road and stress him out or whatever. So when I go home, now the reference counter of that dog is expired, it's gone, right? The dog is gone. So when I come home, I still have a reference, is my point, to this thing that's not there anymore. So when I come home, I'm sad, right? Because the dog's gone. Now, if this was a process and it goes to reference something that's gone, if it's freed, the process is going to crash, like I said earlier. What if my spouse decides to do a different thing and says, I don't think Steve's going to be able to handle the loss of this dog. Let's go to the pound and let's find a dog that looks just like the old dog and hope it fools him. And then I go home and I got a reference to this dog. I'm like, hey, Fluffy, and it bites me, right? Because it's not my dog. That's what we're trying to do. We're trying to replace the object with something harmful, right? But we actually want to maintain or gain control of the process. Or you can use after free from memory leaks and stuff like that as well. So sorry for that kind of rabbit hole there, but I wanted to really show you an example as to how I can best explain what general purpose really means. Some registers do have a more specific purpose in life. We'll get to one of those in a moment. SI and DI are the source and destination index registers. That assembly example on the screen is a good one. Right down there, that it says repeat until 0, compare string, 1 byte at a time, and then we got a pointer in EDI and a pointer in ESI. Now that's AT&T syntax. We'll talk about assembly syntax soon. Most people like Intel, so I purposely put AT&T there. I was kidding. But if you can read one, you can read both. All it is, it's the syntax, the flavor. If you write an AT&T or Intel and you assemble it, it's going to be the same machine code. If you take machine code and you disassemble it into AT&T or Intel, they may look a little different, but it's the same code. So what this is doing, and the reason I said that is because parentheses in AT&T syntax means pointer. Square brackets is for Intel. So there's going to be a pointer in EDI and a pointer in ESI pointing to strings stored in memory. We're going to repeat until we hit a 0, comparing these bytes. And if they match, that means it's true. We're going to set the 0 flag to a 1. That's an example of like string compare right there. Maybe we're comparing a password or apple to orange. It's going to be wrong. It's going to be false. But they can also be used for exactly what I just showed you. These registers could totally be involved in that virtual function call. Or they could hold pointers to input and output buffers for a driver. Now, the stack pointer is one of the registers that has a very specific purpose. Its job, its purpose in life is to hold a pointer to the top of the current stack frame. Now, each thread gets its own stack. And on Linux, in fact, some of them can have their own arena or their own heap subsegment. There's a little calculation, like you multiply the number of processor cores, depending if it's 32 or 64-bit, by another number, and that's how many unique ones you can have. Let's not talk about that. The stack pointer, so if each thread has its own stack, you got a multi-core processor. There's that structure on Windows, for example, called the TIB, the thread information block. Each thread has one. And you can get to it by FS or GS, depending if it's 32 or 64-bit. So if a function gets called, let's say we're in the main function of a C program. The main function is going to have its own stack frame. If main then calls function X is going to go through something called a procedure prologue and epilogue. I'll show you that in a moment. The prologue and epilogue, this compiler inserted code based on the calling convention selected. And that's what's going to build your stack frame or tear it down. So that dynamically happens. As a developer, you don't have to worry about it. So every function call gets its own stack frame. If it's a function that requires a buffer, let's say that we call function X function x needs a buffer because we're going to use a memory copy operation to copy data into that buffer. Then we would subtract some number of bytes from the stack pointer because the stack grows from high memory towards low memory. So when we subtract from it and we adjust the location of the stack pointer, we're allocating memory, or we're tearing it back down. If function x then calls stir copy is going to then copy data into the destination buffer. So that's the job of the stack pointer. The stack pointer is also a coveted register because return-oriented programming is such a powerful thing. And the stack pointer has 3 very specific instructions that are unique to the stack pointer that are super powerful. Push, pop, ret. When you push something, like push EDI, that's going to take the contents of the EDI register and push it onto the stack, adjusting the stack pointer by 4 bytes in that case to point to it. If you say pop and then a register, it's going to take whatever the stack pointer is pointing to, pop that off the stack into the designated register. And then ret, return, is redirecting the flow of execution to whatever address the stack pointer points to, what's stored there. That's the thing that happens at the end of every function call typically, return to the caller. The base pointer had more specific or notable purpose use in 32-bit because the base pointer always points to a static position called the frame pointer for the duration of a function call. And the reason it does that, or did that, is so that you can access local variables and arguments passed to the function. I'll show you how that works in a moment when we look at the stack. On 64-bit, a lot of function calls, you don't need arguments pushed onto the stack or local variables pushed onto the stack because we can utilize registers for that. We've got additional 8 registers, we've got more space. So sometimes you'll see the base pointer used on a 64-bit function call, and sometimes you don't, more often not. So that's the general purpose registers. This is a little diagram showing you what I explained earlier. With those 4 specific registers, AX, CX, DX, BX, you can access lower portions of them. This is just for reference, really. We're not talking about anything here. Those segment registers, I said earlier, have more notable use in like older operating systems, especially older architecture, but some of them do have notable use. You still will see like assembly that says something like call double word pointer DS colon and then something something in square brackets, like, but it really doesn't have much of a purpose in that statement. But FS and GS has some specific use, like on Linux. You'll often see that the GS register, an offset to that in userland, holds the stack canary. So if canaries are being used, you'll see the GS register in play there because there's going to be a read-only variable there that is the stack canary that is going to be pushed onto the stack for every function call that utilizes a canary. Then it's going to get compared and XORed at the epilogue to make sure that the canary has not been overwritten. In kernel mode, like on Windows, the FS and GS registers are going to point to different structures. So I'll give you an example. There's a thing called the process environment block on Windows, which is a structure that has stuff like the heaps, the DLLs that are loaded and their addresses and other stuff. Every process gets one PEB. You can always find the PEB by dereferencing FS offset 30 on a 32-bit system or process, and I think it's GS60 on a 64-bit process in user land. There's always a pointer to the PEB. In kernel land, the PEB is not a thing. You've got something called E process and K process, executive and kernel process. And then from the thread perspective, you've got the TIB in user land for each thread, the thread information block. In kernel land, you've got E thread and K thread, executive and kernel thread. Those are kernel structures. You've also got things like thread local storage, or in the Windows kernel, you've got KPRCB, the kernel processor region control block. It's a massive structure, some of these. If you ever want a good resource, I'll show it to you at some point when it's relevant. Virgilius project, I'll put it up soon, but that is an amazing resource for all Windows kernel structures for all versions. So let's talk about virtual to physical memory address translation now. And I apologize if there happens to be any questions on the Off by One channel. I can't look at that right now. Like I said, I'm in a class, I'm just streaming it in case you wanted to watch for a bit. So virtual memory. Let's talk 32-bit at first. Every process gets 4 gigs of virtual memory. Linux, Windows, Mac, doesn't matter. A portion of that address space is reserved for the kernel, and a portion is reserved for user land. Like on Windows 32-bit default, it's 2 gigs to the kernel, 2 gigs to user land. On Linux default, 32-bit, it's 1 gig to the kernel, 3 gigs to user land. This is virtual memory, though. It's per process. The kernel portion of that memory is monolithic, though. It doesn't matter what process you are under the context of. The kernel memory is going to be the same regardless of the process. But the process can't see that memory because it's in ring 0. That's the kernel's memory. But I'm going to draw something out soon. On 64-bit, you're going to get 7 or 8 terabytes. Like, there's so much memory available in 64-bit. We only use a tiny portion of it because it's enough to give us high entropy ASLR, which is one of the most important reasons for having 64-bit. Things like heap spraying were much more a thing in 32-bit land versus 64-bit land. Think of the analogy, like this room that we're in right now. Let's say we have 20 chairs in it. That's more like 32-bit, where if I said, leave the room, I'm going to pick a random chair, try to guess which one I'm in when you walk in, like before you walk in. You've got a pretty good chance of guessing, versus if I'm in a stadium now and there's 60,000 seats, you're going to have a much harder time guessing which chair I'm in. Now, that's not obviously accurate because it's way more space than that in 32 and 64-bit, but it sets the example. So when you're spraying memory to try to take up lots and lots and lots of heap addressing so that you extend the heap far enough to get to predictable addressing, that's doable on 32-bit. 64-bit is a lot harder because you may only have 32 gigs of RAM, and if you've got access to 7 or 8 terabytes in user land, and I start spraying a couple terabytes of memory, you're gonna have a problem, right? The hard disk is probably not even gonna be able to handle that. So you've heard of paging and swap and all that. Swap's like an old term, like when we swap out there used to be something called terminate stay resident or terminal stay resident, TSR. The old sticky bit, not the Linux sticky bit that says you can't do anything unless you're the owner, you can't delete a file from the folder or something. The old sticky bit meant that a process is not allowed to be swapped out of RAM onto the hard drive into swap space because it's important, it's a critical service or whatever. And in the old days, you would swap entire processes out because you didn't have much RAM. And so we don't do that anymore. We have paging, and part of paging is if there is a process that's kind of getting greedy, it's asking for a lot more memory than it really needs, and maybe you're light on resources because there's so many other processes that need memory, you might page out a portion of that process to disk. But if you go to access a virtual memory address that's been paged out, you're going to have a page fault, and that's expensive. A page of memory is 4 kilobytes. There's also a such thing as 2 meg and 4 meg pages, but 4 kilobytes is pretty much the standard. Every page has a structure associated with it, which is hierarchical. So if you have, let's say you had an NX bit in user land and a page of memory, and you flip that bit to make it so it's executable and writable, if the kernel says that that page of memory is not executable, well, the kernel is going to override what's below it. And so if you get to the kernel and you flip the bit so that page of memory, because you got a PML mapping, goes up to, I think PML 7 is the highest. If you flip the bit in the kernel, great, you can now execute code in that space. That's why we call a critical function like virtual protect to go and change permissions in memory so that gets set accordingly so that I can have code execution there. But if ring -1 at a higher PML mapping says no, that's not an executable page, well, you lose. You're going to have to get to ring -1 to do something about that. So there's those things, right? Let me draw something out now. This is going to be an important drawing. Now, some people ask, well, if it's an important drawing, why don't you have it in the slides or in the book? And that's because it's not something that makes much sense or does much good if it's already been drawn up. So let me draw 3 processes. So we have process 1. Let me grab that so they're all the same size. 2, and then 3. And then let's say the process on the left is Notepad, on Windows, and it's PID number 100. And then the middle one is the calculator process. That's PID 200. And the one on the right is PID 300, and that is Paint, all the classic Microsoft apps. Now, remember what I said. We're going to talk 32-bit, so I don't have to draw as much addressing out. On a Windows 32-bit standard process, let's say it's WoW64 on a 64-bit OS, it's a 32-bit process running. We got the WoW emulator. What's going to happen is 2 gigs is going to go to the kernel, and 2 gigs is going to go to user land. So I'm splitting it right down the middle, or it's supposed to be the middle. And up top, we've got the kernel, and I'll put ring 0. Down the bottom, we got user land, and that's ring 3. We'll talk about where's ring 1 and 2 and all that tomorrow when we get into ring segmentation. But the kernel memory, like I said, is all monolithic. It's the same regardless of the process that you're in. Just like that. I'll copy that so it's consistent. This again means that if I'm under the context of a process in user land and I were somehow able to get into kernel land and I was to look at the memory layout, it's going to be the same memory layout regardless of what process I'm in, because that's the kernel's memory. And there are kernel translation look-aside buffers and all that stuff just like we have available in user land. But in user land, each process has access to the exact same memory addressing. But when you switch between processes that are running at the same time, what's at that location is different. So how is it possible that Notepad and Calc can use the exact same address at the exact same time and something different is stored for each? Because it's virtual memory. What's that register I said earlier that holds the start address of the page directory? Control register 3. So let's say that we go to this address right here. And I'll put it at this, that's the same exact spot in all 3 processes. And we go to that location. And let's say what's there. Well, let's say the address first. Let's say the address is 0x02040830. And in Notepad, what's there is the string monkey. Okay. And then we go to the next process. We context switch over. Notepad's still running, but we context switch over. And we go to that same address now for calculator. So we draw that out. And at that location is the number 42 as an integer. Then we go to paint at that same location. And what's stored there is just some pixel value. So again, I ask, how is it possible that 3 simultaneously running processes can have something different at the same memory address? Because it's virtual is the answer. So the processor is down here. We've been ignoring that. Let's say we got the CPU, and let's say it's a single core, just to keep it simple. So each core has its own set of processor registers. This is a single core. So we've got those registers that we've been talking about. Now, I'm not going to draw them all out, but we'll just draw a few. Let's say we've got EAX, and that EAX is 0. And then we've got EDX, and that EDX is FFFF. And then we've got ESP, and at that is something like 08046600. So imagine all the registers are there. And we're currently under the process Notepad. So I'll draw a line between a CPU pointing to Notepad. We're under the context of Notepad. When we need to leave Notepad and switch over to calculator, that's called a context switch. But before we get there, let's talk about that virtual to physical translation again. So each process, when you're under the context of that process, control register 3 is going to point to the start of the page directory, PD, page directory. Now in 32-bit, each page directory has up to 1024 page tables. So let's say we got page table 0, 1, 2, 3, dot, 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 up to 1024 page tables. And then each page table, let's say page table 2 we're looking at right now, has up to 1024 page table entries, PTE. That's a bad looking E, but that's it. I gotta redraw that E. It's terrible. So up to 1024 page tables within the page directory, up to 1024 page table entries within each page table. What we do to map is a portion, and this is not going to be spot on, but the idea is there. A portion of this virtual memory address is going to point to the appropriate page table for this address. So let's say it points to page table 2. The remaining portion of the address points to an offset to whatever page table entry it's there. So let's say it's page table entry 1 in page table 2. So what's there is going to be the RAM address of where Monkey is stored. And that's why if we context switch over to calculator, we go to calculator's page directory, it's going to be completely different than Notepad. So when we do that translation, the offset into the page table and the offset to the page table entry is going to have a different RAM page. It's going to a different place. So that's how that works from a high level, or sort of low. And then when we context switch now, let's say we need to leave Notepad and we need to go over to calculator. To do that, we have to take a snapshot of the register state. So these registers right there, those are relevant only to Notepad. That's the state of Notepad. And if we have to leave right now, we take a snapshot of those registers and we store it in something called the processor control block, PCB. Also, the PCB has a pointer to the next process that we're supposed to switch to, unless there's been an interrupt to the kernel and things have been changed. So when we get over to calculator, so let's say that we now are no longer in Notepad and we're under calculator, guess what we do? We go to calculator's PCB, we restore the state of the last time we left calculator, and we populate the registers, and now we continue execution. So that's kind of a look at what's going on down there, and that's kind of what paging is. So let's move forward. We've got object files. Now, when you think of a file format like PDF, you have a question? Sorry.
Yeah, so just a so would there be a finite? I know that was one.
Yep.
Very basic, but would there be a finite number of times context switch, or have this piece of memory snapshot?
So I think the question is there a finite number of times that you can context switch and store things in a PCB?
Yeah, like if it's taking that like same space of memory as the pixel that's the number 2.
Right.
Is there a finite number of times that can be snapshotted until you have to free up that?
No. No, I don't. No. There again, there's something called translation look-aside buffers, where when we do that translation, we don't want to go through that over and over again if we're still under the context of the same process. So we're going to store that in kind of like a cache, what's called the TLB, and that way we don't have to do that lookup anymore. But when we context switch, we flush the TLBs. So, but no, there's no limitation. But so let's say you got file formats: PDFs, JPEGs, bitmaps, MP3s. These are all different. There's formats associated with them, right? Oh, sorry, Blake has a question. In the example, the addresses were the same. So how does it look into the different page tables? So that's the lookup, right? So when you're under the context of a process and you look at virtual memory address 02040830 for Notepad, a portion of that address is going to point to a page table within that specific process's page directory. So every process has its own page directory that's unique. So when we do that lookup on the virtual address, we're going to a different spot. So we index into page table 2 in this case, then the remaining offset points to the page table entry where the RAM address is going to be different. Yeah, okay, great. All right, so you got file formats is my point. And when you have a application, like a binary application, like Photoshop, that understands what a JPEG is, it's going to parse through the memory. There are validation routines and parsers that are expecting to see metadata in certain places be certain values, and that's how it's able to render that. If something's corrupt, it's going to complain and not going to be able to do that, or if it's an unsupported file format. Object files, on Linux, you've got ELF, which is executable and linking format. On Windows, you've got PECOF, portable executable common object file format. Mac, you have your own thing. Like, so those are file formats for objects, for binaries. Some examples of segments there are the ones on the screen: code, data, BSS, which is block started by symbol, heap, and stack. There are other types of sections within a binary, like relocation section, the procedure linkage table, like there's all kinds of different areas. PLT is not a great example of that. That's a little bit something else, but these sections are always going to be there. Resource section. So we'll get back to that. Now, when we want to look at an example, let me just draw something out instead of trying to do it verbally. So in the old days, it was always like this. You had a process memory layout. At the top, you had the code segment, CS. It was fixed size and executable. So you've got readable, executable, not writable. Then you've got the data segment, fixed size, which holds initialized variables. So readable, writable, not executable. Then you've got the BSS segment, block started by symbol, which is fixed size. It's writable. It holds uninitialized variables. Readable, writable, not executable. Then you've got the heap that grows from low memory towards high memory. Way down in high memory near the kernel, you've got the stack that grows from high memory towards low memory. And this big void in the middle is called the wilderness. And as long as the heap and stack don't collide, you're good to go. And there should be multiple gigabytes in between that. So they should never collide. On more modern processes, like let's say Windows, for example, you would have it formatted a bit differently. You'd have something like this, where you've got the main thread stack, so MTS I'll call it, and that grows from higher memory towards low memory, but it is in low memory anyway. Then you've got the executable image, and then you've got various thread stacks. So it's multi-threaded, so let's just say we got multiple threads here. So I'll put T, T, T. There's the thread stacks. They grow from higher memory towards lower memory. And then you've got the heap, which grows from low memory towards high memory. And then up here near the kernel, you've got DLLs. It all depends if ASLR is on and many factors, but that's like a different type of memory layout where the heap and the stacks are going away from each other. So these are what those segments are. Let's talk through stack operation real quick. I used to try to do this in one slide, and that was pretty miserable. So now I've got a bunch of slides we walk through. So we've got two different segments of memory, meaning they're in different memory regions, different virtual address regions in the same process. You've got the code segment, which is executable. We've got this instruction pointer that points to the next virtual memory address where code execution will continue. And we've got the instruction that we're currently executing, which is move EAX into EDI. That's actually a copy operation. We're not cut and pasting. And this is AT&T syntax. We are moving from the source into the destination. Copy EAX into EDI. That's all we're doing. Over on the right, you see the stack segment. Every thread gets its own stack. We only have the main thread stack there. You've got the base pointer and the stack pointer. Stack pointer always points to the top of the stack. We grow from high memory towards low memory. We go to the next instruction. Push EDI. Take the contents of EDI, push them onto the stack, adjust the stack pointer accordingly so it subtracts and points to what we just pushed onto the stack. Remember, we subtract because we're growing from high towards low. It's reverse. Then we call a function. When we call a function, two things are going to happen. First, we take the next virtual memory address, which is where the instruction pointer is pointing, where execution would have continued, and we push that onto the stack, adjusting the stack pointer. That becomes the return pointer. That is how we get back home. When When we call a function, we want it to return control back to us. The second thing the call instruction does is redirects the flow of execution to the called address. In this case, it's function X. Then we get into something called the procedure prologue, compiler inserted code. This sets up the stack frame for the called function. Function X gets its own stack frame. It gets built on top of main's stack frame. So the first instruction in the procedure prologue is we take the address stored in the base pointer and we push that onto the stack. That becomes the saved frame pointer. We adjust the stack pointer accordingly. Why do we do this? Because just like we used a return pointer to return control back to the caller, we used a frame pointer, which is the base pointer address pushed onto the stack prior to adjusting it, so that we can restore it later on. You'll see what's about to happen now. We have now copied the stack pointer address into the base pointer. We've stolen it away, pivoted it away from where it was pointing inside the main stack frame. But that's okay, because for the duration of this function call, the base pointer is going to point to the frame pointer. And eventually we're going to pop that back off to restore the base pointer. The reason that we have the base pointer being used in this example, this is a 32-bit example. It could also be a 64-bit example, but more than likely the argument would be in a register instead of pushed onto the stack. But the reason we have the base pointer in this case is so that we can reference that argument that was passed. We pushed the argument onto the stack, which is the contents of EDI. We now know where it is because we can say EBP plus 8. That's where we know the argument is stored. If we had two arguments, EBP plus 8 and plus 12. 3, keep going. Plus 4 from the base pointer is going to be the return pointer. We know where things are based on a static offset from where the base pointer points, which is always to the frame pointer. In this case, we're now allocating a buffer. We're subtracting hex 20 or 32 bytes from the stack pointer, adjusting it accordingly. Now we've got a buffer. We could copy data into there if we want. So at this point, we've built the stack frame, allocated a buffer, because this function needs one for whatever reason, and we're going to execute the code related to function X. Once we're done, when function X is done doing whatever it was supposed to do, we need to tear down the stack frame and restore everything. This is the epilogue of the function. The first thing that happens, we copy the address of the base pointer, which points to the frame pointer, into the stack pointer, pulling it back down, deallocating the buffer. The stack and the base pointer now both point to the frame pointer. Then we pop the frame pointer off the stack into the base pointer to restore it back where it pointed before we called the function. Now the stack pointer is pointing to the return pointer, because each time we pop, we add 4 to the stack pointer, or 8 if it's 64-bit. Then the final instruction here, ret. We redirect the flow of execution and return back to the caller. Now, a quick question though. Do we still need to point here? What does that mean? Look over on the right. The stack pointer, after we return to the return pointer, advanced forward 4 bytes in this case, because that's what it does. It's now pointing to the old argument that we no longer need. We don't want it pointing to that. So we need to adjust that. We can do it one of 2 ways depending on the calling convention. We can either do a ret4, or we can return back and have an instruction that compensates. So let's do the ret4 first. Normally we just do a return, meaning the stack pointer would advance 4 bytes like it normally does. If we say ret and then a value, that means we're telling the stack pointer how many additional bytes to advance. If we say ret4, we're advancing over the old argument. The other way to do it would be to return back to the caller, and the first instruction when we return back would be to add the number of bytes in relation to the arguments pushed so that we advance the stack pointer that way. 2 different ways of doing it. One is cdecl and the other is standard call. cdecl expects the caller to tear down the stack. It's more polite. It says, hey, you made dinner, let me clean the dishes, right? Standard call says, you made dinner, clean up the dishes too. We expect the called function to clean up after itself. The calling convention is selected, at compile time. You can choose which one, but there are obviously requirements as to when you need to use one versus another. Some calling conventions support function overload, which would mean something like different data types as arguments or a variable number of arguments. Other calling conventions don't support that. It also determines how something is stored into memory in obviously little endian or, well, if it's x86, it's little endian architecture. So it's not big endian. So bytes are stored in reverse order. What I meant to say is the way that arguments are stored in memory. So GNU Debugger is the debugger we're going to be using today. We're going to use a extension. There's extensions like PETA with the Python Exploit Development Assistant, as well as Jeff, which is another great one. Jeff is seen as a more feature-rich one, but PETA is also good. And it's a debugger, so it allows us to attach to a process and look at the memory, patch memory, view the call stack, look at the registers, all the things we want to do. I'm not going to go through each of these commands because we're going to be using them, and I will show you as an example as opposed to talking about them here. But these are some common commands that you're going to use, like BT or backtrace to look at the call stack, or C for continue, or SI for step 1 instruction, which sets the trap flag, or info registers, which dumps the processor registers. So we'll get back to that in a moment. I'm going to show you GDB here in just a moment. So first, before we get there, we're going to see a lot of assembly now. Disassembly, which is taking the machine code, the opcodes, disassembling them into their mnemonic, because it's easy, it's more human readable. Now some will look at assembly and be like, that's not readable. I want a decompiler to get it back to pseudocode, which is fine. Assembly, why would we write a program in assembly? Because it's powerful, because we get to tell the registers exactly what we want them to do and not to do. If the compiler is making decisions that we don't like, in C, we could do some inline assembly. We don't have to write in pure assembly. We could have some inline assembly in C. In higher level languages, you can't do that. Memory is managed on your behalf. These low level languages are powerful. You manage memory, which can get you into trouble. Memory corruption bugs are a big thing, obviously, with low-level languages, which is why languages like Rust are out here to save the day, right? So drivers, video games, things where speed is important as well, because sometimes compiler will insert weird things that aren't needed. And you'll see instructions that, they're like, why is it doing that when it could have skipped that instruction and just done this instead? Compiler did it. If you don't like it, write assembly. There's AT&T and Intel syntax. What we've been seeing so far is AT&T. What we'll be working in primarily is Intel. If you can read one, you can read the other. The main thing that's the difference between the two is source and destination operands, if there are two operands, are reversed or switched. An AT&T on the left, you would read this instruction as subtract immediate operand. So AT&T uses $ and %sign to indicate an immediate operand, like a literal operand, or an indirect operand in a register. So we're saying subtract this from that operand. So we're subtracting 48 bytes hex from the address stored in the stack pointer. In the Intel flavor, the same instruction, we reverse the operands. So instead of subtract this from that, it's subtract from this that. So we switch the operands if there's two. Other differences include AT&T uses $ and %sign for immediate and indirect operands. It uses parentheses for pointers, as where Intel uses square brackets for pointers, and it will spell out things you'll see in a moment. This instruction on AT&T is the exact instruction. It's the same instruction in Intel right there, but it's way different looking. The top one, we say move the long 32-bit, move the long immediate operand. So take this literal address and write it to the top of the stack. How do I know top of the stack? Well, parentheses are there. That means it's a pointer. So go to the address stored in the stack pointer and write this there, put that there. How do I know it's the top of the stack? Because it says %ESP with no operand value next to it. If it said ESP +4, we'd go to the top of the stack, +4 bytes, and then write that argument or that value. Down below, it says move into the top of the stack, and notice it says D-word pointer as opposed to just the parentheses. It's literally saying move the double word pointer, square brackets, ESP, move into the top of the stack, that. The last thing we're going to close out here, and I'll get a chance to show you the debugger as well, is linking and loading. So we're less interested in loading in this regard with exploitation right now than we are with linking. Linking is when we dynamically compile something. We typically don't statically compile our binaries because it's making it unnecessarily large, and it's also permanent then. If you compile library code into your binary and all dependencies are compiled in, it's static, then if there's any vulnerabilities in those libraries that are discovered, that thing traveling around will always be vulnerable. As opposed to dynamically linking it, then I have dynamic dependencies on libraries that I expect your system to have when you run my program on your system. I need kernel 32, or I need libc so.6 or whatever. So we load the library, and then we link the functionality that we have a dependency on. So that's called symbol resolution. Relocation happens when an address is already taken and something else would like to be loaded there. We need to relocate it, patch it, fix it up. So in Linux, it's ELF. Tomorrow we'll talk about PECOF, executable linking format. There's shared objects, which are like DLLs on Windows, that's the libraries. And then there's just plain old executables like ping or Wireshark. On Linux, the way that we do the resolution is through these tables called the global offset table and the procedure linkage table. Don't ask me why they designed it this way. I just know that they did. I'm just going to talk about it first, and I'll show you in the debugger. These tables are used when you have dynamic dependencies and you have to link. Think about this real quick, static versus dynamic. If I told you I cook great Thai food, you're like, oh, you want to come over and cook? And I'm like, sure. And I come over and you hear a truck backing up outside, and then you open the door and I'm like unloading ovens and tables and cutlery and everything, and even a portable potty, right? Everything I could possibly need. That's statically compiling it. Versus if I just show up with a bag with the ingredients I need, I expect you to have the dependencies like a stove and tables and cutlery. So I just need I need to link it though. When I get to your house, I say, where is your kitchen? It's there, linked. Where's your stove? There, linked. And I might do something called lazy linking, which means don't ask for something until you need it. The problem with lazy linking is there's a mitigation called rel-row. Sounds like Scooby-Doo, but relocation read-only. Rel-row. I tried. So, and that will harden the table by linking everything right at the start of the process and then turning off the write permission. Because write what where vulnerabilities allow you to overwrite pointers inside the global offset table, which then anytime the function gets called that you've overwritten now in the table, you get code execution. So the way they did it is you'll see in a moment when I go into GDB, when we call strcpy or printf, it'll say @plt. That tells you it's dynamically linked. So that says go then, instruction pointer, to printf's entry inside the procedure linkage table where there's going to be a jump instruction to a pointer in the global offset table entry for printf. Every dependency gets its own entry in the PLT and GOT. So we say jump or call, let's say call printf at PLT. We go to printf's entry in the PLT, and then there's going to be a jump to the pointer in the global offset table entry for printf. The first time we're linking it or calling it, it's not yet linked, so it's going to send us straight back into the PLT where we're going to call the dynamic linker, and it's going to link it for us, writing it to the GOT, and then we're good. Let me show you how this works inside the debugger. I'm going to use a tool called objdump as well, which is a dead listing tool. It produces dead listings or disassemblies. And I'm going to use it so that I can see the dynamic dependencies. I'm on a Linux box right now, obviously, and I'm going to zoom in a little bit for you. And if I say, I'm going to go into a little folder with a program called password in it. If I say objdump password, oops, I forgot to say -R, that shows me the global offset table for this program. I can see all the dynamic dependencies right there. Strcpy, printf, gets, puts, exit. So we can take an address like the one for gets. I'm going to grab that address for gets, 804.8.A014. Now ASLR is not on right now. Actually, let me verify that. We're going to turn ASLR on in a bit. For right now, we're just learning. So sudo -I, and then I'm going to say echo 0 into /proc sys kernel randomize VA space. And now if ASLR was on, it's off now. So we go into the debugger, GDB. For right now, I'm going to turn off the extension and just show you raw native GDB. Password. Okay, so we've loaded the program into GDB, and I got that address, right, that I took from the global offset table entry for gets. We can look at the procedure linkage table by saying info functions. Any function that says at PLT is a dynamic dependency, like there's gets right there. That address is gets entry in the procedure linkage table. And then this address, if I say X to examine a hex double word, starting at that address, which is the global offset table entry for gets, what's there right now is this address. That address actually is really close to this address. It's 6 bytes away, right? That's because we haven't yet linked it. When we link it, that address will be the real one for gets in whatever library it's in. So I'm going to set a breakpoint on the call to gets. So we're going to say disassemble main. This is the main function. You see the virtual memory address and the code segment on the left, the offsets, and then you see the instruction, and then you see the operands. We don't see the opcodes right now, but you can see those too if you say disas/r main. Now you see the opcodes. It doesn't put them there by default because it kind of messes the screen up. But notice how some of them are 1 byte, 2 bytes, 3 bytes, 4 bytes, like it's variable length. And right there, look at that, there's a C3 instruction. That by itself would be a return, but right now it's being interpreted as add this value to whatever's in EBX. So if I grab this address and I say examine the instruction at that address, it says it's the add instruction. If I say +1 and I index in 1 byte, it's a return now. That's how return-oriented programming works, and that's why we find gadgets. We look for C3 bytes, and then we iterate backwards based on a depth that we set, and we see which instruction sequences still end with a return instruction. We'll get to that stuff more later. So if I say there's a call here, there's a call to the function called check password, and it has no PLT next to it, meaning it's not a dynamic dependency, it's an internal function. So I can say disassemble check PW, and now we're disassembling that. Notice the procedure prologue right there at the top. Remember we talked about that? Here's that call to gets right there, and it says call gets at PLT. So I'm going to set a breakpoint on this address. So we'll say BP for breakpoint, paste that in, hit enter. Sorry, break. I'm not in WinDebug. Pending future library load. Yeah, sure. We'll see if that works. So I'm going to say run now. We're running the process, and it says please enter the password. So it looks like I didn't get my breakpoint in that case, but please enter the password. If I enter it, it just says access denied. We didn't get it, right? So info break. I can see that breakpoint I put in there. So I'm going to say delete break 1. And let me take a look at that again. So here is that address, and we set that breakpoint. I don't know why it didn't break there. Oh, I forgot to put an asterisk in front of it. An asterisk means a pointer. I'm glad I made that mistake because it's important. If you're breaking on a function name, you don't have to put a pointer unless you're doing an offset. But if you're breaking on an address, you got to put an asterisk. So we do that. Now it's going to work. Run, and we hit the breakpoint. What's the instruction right now? It's call gets at PLT. So if I say SI, step 1 instruction, we're now in the procedure linkage table entry for gets. And it says we are basically going to go now, if we want to look at the instruction there, XI, EIP, jump. So one more time, take a step back. We were in the check PW function. We did call gets at PLT. We are now in the procedure linkage table entry for gets. And right there is the instruction, jump to the pointer stored at the address for gets in the global offset table. We just looked at that address a little earlier, remember? It's right here. There it is. And that's what's stored there right now, which is only 6 bytes away from where we're currently at. That's because it's not linked. if we step instruction, we're going to go to that address. Now we're at A3886. We're going to call the dynamic linker. So if I step instruction a few times, you can see we're going into a shared object. We're going to call the dynamic linker. It's going to write the real address for gets to the entry for gets inside the global offset table. So if I say C to continue and I break, Control C forces a breakpoint, and we look at it now, that's what's stored there now because it's been linked. So if we take that address and we say x/8i, examine 8 instructions, starting at that address, you can see it's the real gets function. That's how linking works. Now you should be able to see that if I was able to overwrite gets entry in the global offset table, anytime gets called, we get code execution. We can also say BT to look at the call stack, and we can see how we got to where we are and how we return back home. So I know that's a lot of information. This is just a walkthrough of what I just showed. But that's a lot, right? And all this stuff should stick in your memory, not maybe all at once. You go back and read stuff, and as you work on this today, tomorrow, and going forward, this memory will come back to you, and you'll get used to it. We're going to go through lots of assembly today and tomorrow and the next day, so you'll start to feel really well versed in it, hopefully in a couple days, if you don't already have experience in it. But things like you might say, like, well, why do I care about linking? Well, I just told you, because if we can overwrite a pointer inside the writable global offset table, then we can get code execution when it gets called. Now we just need to find a write what where primitive, which we're going to start working on this stuff going forward. So that is the end. We're going to take our 20-minute break, and we'll come back and get into shell code. So thanks to everyone who is watching online as well.